Hello everyone, we're back for another daily coding video. I believe today is day 17. It is February 1st at 1:36 p.m. Today is a Saturday. So I think I'm going to try another tree problem today, medium tree problem. Haven't seen this one yet, so we'll try binary tree right side view. Okay. You are given the roots of a binary tree. Return only the values of the nodes that are visible from the right side of the tree, ordered from top to bottom. Okay, so we want to return a list. Okay. I don't know if I'm crazy. I'm probably crazy. So I could say, so we want top to bottom. Okay. So current equals stack.pop. So this is of type node. So if we want top to bottom, we'd want to add this one and then this one. Yeah, so we could have result and we can say result.append current.val. So we should assume that root will always be, or the stack will always be non-null. So if current.write, then we'll say stack.append current.write. And then this should give me an error because this will be none because I'm not checking. I need to return. Okay, so let me just deal with that. So if not root, then we want to return an empty list. All right. Oh, I see. So the problem's not just returning all the right nodes. Okay, I thought that seemed too easy. So if we have, what is it? 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. We should return, in this case, 1, 3, and 7. But for instance, if we have this, should we return 1, 3, 6? I believe so, because we have 1, 2, and we're only returning 1, but 2 would also technically be visible from the right side. Okay, so assuming that this tree should output 1, 3, 6, and this tree should output 1, 2. Another way of kind of looking at it is that every level has a rightmost element. So either a level can be complete or incomplete. Okay, so let's assume this one's always complete. So this next level, if we do like a BFS there, and then in our queue we add 2 and 3. So after the for loop, so because this completed both of its neighbors, but we could also have something like this, for instance. So let's say 5, like that. Also, does it have to be binary search tree? Just as binary tree, and O of n, O of n. Okay, so in this case, we would want this. So here I'm thinking you might actually need a breadth first search. And then it's just a matter of determining the rightmost position. So maybe every node can have like a value of rights of like R. So this one would have 0 R. This one has 1 R. This one has 0 R. This one has 0 R. This one has 1 R. And then, for instance, if you had something here, you would then, like, let's say 6, this would have 2 R because we moved to the right twice. And then we just, if we check if this R counter is the greatest of everything in the level, then we add it. So the problem with this would be if we have something here, for instance, let's say 5, actually let's say 4, this R counter is also 1. So if we got rid of this, then in this case we would have 2 with the same count. Alternatively, what you could do is just add everything in a layer, and just the most recent one that you add from left to right is the most right. So I think that might be a better way of doing it. So let me try a BFS here, because I think you need it to be a very specific order that you explore it. Because if you do DFS and with the right counter, you can end up with situations like this. But maybe it would be fine if we just do left and then right, because the DFS here would go those 3, then this one, then these 2, then this one. So a DFS here would probably work too, if we just store the right counters and say if it's greater than or equal to the right counter, then we're fine. But we would also have to store the heights or the level that it's on, which might get tricky. So I think I'm just going to do BFS because that's the like human way I would do it. Okay, import deck. So we're going to say, I'll just comment that out for now. So Q equals collections.deck with root. Okay, while Q, then we'll also have a result list, which will be our final result. So we want to say current equals, so I'm going to try to just ignore the R counters and do it based on the last thing that you explore, going left to right. So current equals Q dot pop from the right. And then we can say for neighbor in current.left, current.right. And then I guess I could have something called most recent encounter. Okay, well, if I have this tree, you'd start here. So you'd pop this one, and then add 2 and 3. And then you would, well, it would actually look like this. And then you would pop this one. And then you would add so we need to know when the layer has been so with each of these we could have tuples, so it's like to tell when we've changed height. So for instance, we would have 1, which is level 0. We pop that, and then we add 2, which is level 1. And then we append left 3, which is level 1. Then we would remove this. And then our queue would be so 3, 1, 5, 2, and 4, 2. And what we could do is every time we pop, if the previous height does not equal the current height, then we know that we've gone up a level, so we want to add this value. So I'll try that. Okay, so we're going to add a root and then the level 0, current and level. So we'll say node. So this will give us the nodes. So we want to add it to the queue. So queue.append left, neighbor, and level +1. Okay, and we also want to set previous level to level. And here what we could say, after we pop something, we can say if previous level does not equal level, then for now we'll print level change with node.val. Most recent encounter I don't think we need. So here we would just like append to result. But we'd have to store the previous node as well, which would be fine. All right, so let's just print node.value. And we also want to say if these are null, then don't append it. So if neighbor okay, so let me run this. And I just want to see whoops. Previous level. Okay, we'll just return an empty list for now. Okay, so 1, 2, yep, 3. Okay, so here, if we look at this one, 1, 2, and then that changed the level. So we would want to add 1. And then 4 also changes it, so we'd want to add 3. And then 7. We also want to just add the last node as well. That the last one we see will also be rightmost as well. Okay, so here what we want to do is we probably want so previous node equals none, and then here we'll say previous node equals node, and here we will append, so res.append previous node.val. I'll keep this print statement here. Okay, so if I run that, I don't think I'm doing anything with the res. So if I return res, wrong answer. Oh, also after the queue, I want to say res.append node.val. Okay, so will this work with nuns, or will we have... Okay, it works with nuns. Okay, cool. So, all right, let me get rid of the print statements and clean this up a little bit. I don't know if there's an easier way to do this. So here, like, we detect change in level, and if there is a change in level, then we add the previous node. Okay, so I'll say if change in level, add last seen node. This makes sense to me. This makes sense to me. Okay, so if I look at the solution here, so binary tree right side view. Let's see what they did. Depth first search. Okay, so variable right side and queue length. So we iterate through the queue and pop from the left. Okay. So we get the next in line. If it's not null, then we say right side Okay, so right side. Oh, okay. So it basically gets the last one in line. And appends. Well, it just appends all of them. And then... Okay. That kind of makes sense. And then this one looks a lot easier. Alright, so it uses this trick to detect it. So it basically just DFSs with the depth. And then if the depth equals the length of your results, then you append the value. So if I have 1, 2, 3. Oh, okay. So here the depth is 0. So we append 1. And then we DFS with the rightmost node. with a depth of 1. Oh. So that even works with here? Yeah, because it would just return. Okay. Well, I don't think this part has to be in the video, but thanks very much for watching. And yeah, this is my solution. It seems like it could have been a lot shorter, but I'm happy with it. And I'll see you guys tomorrow.